Hi students, today's topic is heat and temperature. First, let's define the temperature. Temperature is a measure of the average kinetic energy of the particles in a sample of matter, expressed in terms of units of degrees designed on a standard scale. Now we have two objects, A and B. They are made of the same material. We understand it because their particles are identical. The length of these arrows represent the velocity of the particles. So you see that the velocity of particles A is bigger than B. Thus, the kinetic energy average of A is bigger than the average kinetic energy of B. So I can say that the temperature of A is bigger than the temperature of B because temperature is just related to the average kinetic energy of the particles that made the matter. One of the thermodynamic properties of a system is its internal energy. The internal energy is the sum of the kinetic and the potential energies of the particles that form the system. So internal energy is the total kinetic energy plus the potential energy of the particles. So you have to think of this in micro scale. For example, does a glass of water sitting on a table have any energy? It may seem to have no apparent energy on microscopic scale, but in microscopic scale, the particles are vibrating, so they have kinetic energy, and there is more molecular attractive forces between the molecules, and this forms the potential energy. So a glass of water has internal energy which is equal to the kinetic energy of the water molecules plus the potential energy of the water molecules. So it has an energy. As we have mentioned before, the first law of thermodynamics states that the energy of the universe is constant. Energy can be transferred from one system to its surrounding or vice versa, but it can't be created or destroyed. So the change in the internal energy of the system is equal to the sum of heat gained or lost by the system and the work done by or on the system. So heat is a form of energy, but heat is a transfer of energy. So I can say that heat is the change in internal energy. Change in internal energy. How much your internal energy increase, this is how much you gain heat. How much your internal energy decrease, this is how much you lost heat. In this example, we have two objects. A is touched to B as in the figure. However, the change of their temperatures. When there's a contact between objects, there's a heat transfer. I see that its particle's velocity is more, so the temperature of A is bigger than the temperature of B. So when they touch each other, there will be a transfer of energy from hot object to a cool object. So A will lose heat, so the temperature of A will decrease, and B will gain heat and the temperature of B increase. So which one will lose internal energy? A will lose internal energy because its temperature is higher. So B will gain this energy because its temperature is lower. We have two identical glasses. They contain equal samples of water. Let's say they have both mg of water. The water in glass A has twice thermal energy as the water in glass B. So let's say the internal energy of B is this, and A has twice the internal energy of B. So we're going to compare their temperatures. The internal energy is related to the kinetic energy plus the potential energy. As they have the same mass and they are both water, so I can compare their potential energy. but I can compare their kinetic energy. As the internal energy of A is bigger than B, that means that the kinetic energy of A should be bigger than the kinetic energy of B. Thus, that means that the temperature of A should be bigger than the temperature of B. Two identical glasses contain different samples of water. Glass A contains 500 milliliter and B 250 milliliter of water. So I can say that this has m gram of water and this has 2m gram of water. The water in glass A has twice the thermal energy as the water in glass B. We said that the internal energy is equal to kinetic energy plus the potential energy. Kinetic energy is equal to 1 over 2 mv squared, so related to mass, plus the potential mg8 related to mass. As the mass is doubled, so I can say that the internal energy is again doubled. So I can say that the average internal energy of A is equal to the average internal energy of B. So the kinetic energy of A average should be equal to the average kinetic energy of B. That means that they should have the same temperature. Why it has more internal energy? Because its mass is more. Two different glasses contain different samples of water. A has 500 grams of water and B 750 grams of water. So I can say that it has 2m and B has 3m gram of water. The water in glass B has twice the internal energy as the water in glass A. So again, the internal energy is equal to the kinetic energy plus the potential energy. So the internal energy is doubled. If it is related to mass, so mass should also be doubled. But I see that the mass of B is not twice the mass of A. It is less. So what makes the internal energy more than A is temperature, is average kinetic energy. So the average kinetic energy of B should be bigger than the average kinetic energy of A. That means that the temperature of B is bigger than the temperature of A. So the temperature of A is less than the temperature of B. Now we are going to cover temperature scales. We're going to cover 3 temperature scales, and the last one will be yours: Kelvin, Celsius, and the Fahrenheit scales. The beginning part represent the freezing point of water or the melting point of ice, and the end of a thermometer represent the boiling point of water. In Kelvin scale, the freezing point of water is 273 Kelvin and the boiling point is 373 Kelvin, and we have 100 sigmas. In Celsius case, the most known one, the freezing point of water is 0 Celsius and the boiling point of water is 100 Celsius. Again, we have 100 sigmas. In Fahrenheit scale, the freezing point is 32 Fahrenheit and the boiling point is 212 Fahrenheit, and you see that it has 180 sigmas. Let's see my thermometer. It represents the freezing point of water as minus 10S and the boiling point as 110S. So you see that there are 120 sigmas. So in order to convert the one scale into another, we use this formula. The read value, let's say K, minus the freezing point 273 over the number of segment 100 is equal to in all thermometers. So the read value in Celsius minus 0, you don't have to write it, over the number of segments equal to the read value on Fahrenheit minus the freezing point of water over the number of segments. The read value in my thermometer S minus the freezing point minus 10 over the number of segments. We use this formula in order to convert one scale into another. We simplify it. If you want to convert Kelvin to Celsius, you can say Kelvin, this cancel each other, is equal to Celsius plus 273. If you want to convert Celsius to Fahrenheit, so Celsius is equal to 5/9 times Fahrenheit minus 32. The 0 point on the Kelvin scale is known as the absolute zero. It's the lowest temperature, the minimum energy that can be achieved. The concept of an absolute temperature minimum was promoted by the Scottish physician William Thomson, as known as Lord Kelvin, in 1848. Thomson theorized based on the thermodynamic principles that the lowest temperature which could be achieved was 0 Kelvin or minus 273 Celsius. The sensitivity of a thermometer depends on four concepts. One, the coefficient of expansion of liquids we use, how easy it expands, the increased sensitivity of thermometer. The width of the narrow, as it is narrower, it is more sensitive. The width of the bulb, where the liquid is put, if it is bigger, then it is more sensitive. And the number of segments for the scale, if it is more, then it is more sensitive. Now let's do an example. Minus 40 Fahrenheit is equal to how many Celsius? So minus 4 minus 32, I'm applying the formula, over the number of segments is equal to Celsius over 100. So when I cancel this, it is 5 to 9. This equal to 72. 72 over 9 is equal to, it has minus also, minus 8. So minus 8 is equal to Celsius over 5. So Celsius is equal to minus 4 degree. You see that at minus 40 degree, they show the same number. Now convert the Kelvin into Fahrenheit. 253 Kelvin minus 273 over 100 is equal to Fahrenheit minus 32 over 180. And I cancel this each other, 5 to 9. This equal to minus 20. Minus 20 over 5 is equal to Fahrenheit minus 23 over 9. This is minus 4. So Fahrenheit minus 32 is equal to minus 36. So Fahrenheit is equal to minus 4 degree. Here we have X and Y thermometers. We're going to convert 20 X is equal to how many Y. So you see that the melting point of X is minus 10. So the read value is 20. 20 minus 10 over the number of segment is 90 is equal to the value read on Y minus the melting point 20 over number of segment 120. So when we cancel this with each other, 3, 4, this equal to 30. So 10 is equal to minus 20 over 4. Y minus 20 is equal to 40. So the read value of Y thermometer is equal to 60. We said that heat is the transfer of energy. It is the change in internal energy. So you transfer heat from hot objects to cool objects. Heat is not something that is contained in an object. So we can say that I have heat. My heat is more because it is not contained or deposited in an object. It is an energy that can be transferred and changed into internal energy as kinetic or potential. The unit of heat is joule or calorie, and 1 calorie is equal to 4.18 joules. This is a typical heating curve for water. You see that there are 5 segments. In this segment, the state of matter is solid, it is ice. Let's say at point A, it is solid. Here comes to melting point. Let's say the point B is still solid. At this region, it is melting, so found in solid plus liquid. At exactly the point C, it is totally melt and become liquid. Now here the temperature of the liquid arises, come to the boiling point, and it is also liquid. Here it evaporates and the state is liquid plus gas. At this point it is totally evaporized, so become gas, and then the temperature of the gas increases. So you see that at the vertical graphs there are phase changes, and in other graphs there are temperature changes. Specific heat capacity is the amount of heat required to cause 1 unit of mass to change its temperature by 1 degree centigrade. You see here in the table that the specific heat capacities of some matter. Its unit is joule per kilogram Kelvin or calorie per gram degree centigrade. What it means, let's give example from water. The specific heat capacity of water is 1. That means that you have 1 gram of water at, let's say, 20 degrees centigrade. In order to change 1 gram of water, increase its temperature by 21 degrees centigrade, the amount of heat you needed is 1 calorie. This is what specific heat capacity means. You see that from the table, the specific heat capacity of water is very high compared to other substances. So that means that water can store energy longer than most other substances. These are some examples in our daily life. For example, the Gulf of Mexico remains warm during the night when air and soil temperature decrease rapidly. Why is the southern hemisphere summer generally not warmer than the northern hemisphere summer, although it's closer to sun during the southern hemisphere summer? Because most of the southern hemisphere is water, which regulates the seasonal temperatures. The specific heat capacity provides a means of mathematically relating the amount of thermal energy gained or lost by a sample of any substance to the sample's mass and its resulting temperature change. So we have the formula, the heat gain or lost is equal to mass times specific heat capacity times the temperature change. Q is the heat in calorie or joule. M is the mass in gram or kilogram. C is the specific heat capacity in unit calorie per gram degree Celsius or joule per kilogram Kelvin. And this is the change in temperature in Celsius or Kelvin. What quantity of heat is required to raise the temperature of 450 grams of water from 15 to 85? The heat is equal to mc delta T, mass 450 times specific heat capacity 1. The temperature change is 70, which is equal to 31,500 calories. 1,200 joules of heat is given to 100 grams of lead at, it should be 10 degrees centigrade. Find the final temperature of lead. The specific capacity is given as 0.03 calorie. As it is given in calorie, I should convert joule into calorie. So 200 joule over 4 is equal to approximately 300 calorie. So heat is equal to mc delta T. The heat taken is 300. The mass is 100 times specific heat capacity 0.03. So I'm going to find here delta T. The delta T is equal to, this will be 300 degrees Celsius. So delta T is equal to the final temperature minus the initial temperature. 100 is equal to final temperature minus the initial 10. So the final temperature will be equal to 110 degrees Celsius. The temperature graph for A and B is given. We are going to find their specific heat capacity ratios. The mass of B is 3 MA. So if I put M for A, then B is equal to 3 M. Now I see that both of the substances take equal amount of heat equal to 300. So I can say that the heat taken by A is equal to the heat taken by B. So MaCA times the delta A is equal to MbCB times delta TB. MAM times Ca, the change of temperature of A is from 5 to 35, 30. Mb 3M times Cb, the change of temperature of B is equal to from 5 to 15, 10. So M cancel each other, 3 times 10, 30 cancel each other. So Ca is equal to Cb, so their specific heat capacity ratio is equal to 1. We have another term, the latent heat of fission. It is the amount of heat needed to melt 1 gram of any substance, or the heat released when 1 gram of any substance freezes. What does this mean? The latent heat of fusion of ice is equal to 80 calories per gram. So when you take 1 gram of ice at 0 degrees centigrade, and in order to melt and change it to 1 gram of water at 0 degrees centigrade, the amount of heat you need is equal to 80 calories. This is what it means. The opposite is also should be considered. That means that when 1 gram of water freezes, it releases 80 calories of heat. The latent heat of vaporization is the amount of heat needed to vaporize 1 gram of any substance, or the amount of heat released when 1 gram of any substance condense. Now, the latent heat of vaporization for water is 540 calories per gram. When you take 1 gram of water at 100 degrees centigrade and change into 1 gram of vapor at 100 degrees centigrade, you need 540 calories. Or when 1 gram of water condense into liquid water, then 540 calories of heat is released. Evaporation is a cooling process while condensation is a warming process, because when something evaporates, it takes heat from its surrounding. So the surrounding loses heat and becomes cool. When something condenses, it gives heat to the surrounding. So the surrounding takes heat and gets warmer. We have covered this heating curve. Now put the formulas. In the first section, there's temperature change, so I'm going to use the formula mc delta T. In the melting process, I'm going to use the formula m times LF. Increased temperature of water, the formula mc delta T. In boiling, m times latent heat of vaporization, and increased temperature is gas, mc delta T. Let's calculate the quantity of heat required to melt 50 grams of ice at 0 degrees centigrade. The heat is equal to m times LF, heat needed to melt 50 grams of ice, 50 times latent heat of fusion 80, which is equal to 4000 calories. I have an ice cube at a temperature of minus 20, put in a plastic bowl and place in a micro oven and turn on the micro oven. When the oven is turned off, the bowl contains water at plus 60 degrees centigrade. I'm going to draw the heat temperature time curve. So first it will go to melting point, come to 0, the melting point of ice. It will melt, become water, and then the temperature of water increase and come to plus 60 degrees centigrade. Suppose we heat sample A, which is 150 grams of ice at minus degrees centigrade, and we have a sample B. It is also 150 grams of ice at 0 degrees centigrade. Both put in the same microwave until they become water at 30 degrees. So the time taken to heat sample A will be longer, shorter, or equal to B. Now the A first will come to 0, melt, and then become water at 30 degrees centigrade. But B, it is already at 0, so just melt and then become liquid water at 30 degrees centigrade. So you see that the time elapsed for A should be bigger than the time elapsed for B. When different substances with different temperatures are in contact or mix, the substance with high temperature lose heat and the other with a low temperature gain heat. We have covered this. This is because the first law of thermodynamics states that energy lost during one process must be equal to the energy gained during the other process. So the heat given by an object in contact should be equal to the heat taken. The heat transfer continues till the substances have the same temperature, which we call this situation the thermal equilibrium. For example, we have two objects, M1 and M2. They are in contact. So the temperature of M1 is bigger than the temperature of M2. So the transfer of heat will be in this direction. So M1 will lose heat and M2 will gain heat, and the heat lost by the M1 should be equal to the heat lost by the M2. The temperature of the mixture will be smaller than the higher temperature and bigger than the lowest temperature. So in our example, 70 should be bigger than the temperature of mixture and it is bigger than the lowest temperature, 40 degrees centigrade. Let's examine this graph. There are two objects with 5 and 70 degrees centigrade. They mixed and the equilibrium temperature is reached at 30 degrees centigrade. You see that the graph is not linear, it is a little bit curved. This is why, because over time the temperature difference between the system and the surroundings decrease, the rate of the heat transfer also decreases. This is why we have a gentle slope of two lines. Two glasses each contain the same 500 milliliter of water. A has a temperature of 66 and B has a temperature of 94. They are mixed together, so the final temperature, if the masses are equal, then the thermal temperature will be equal to the average of their temperatures. So here 66 plus 94 over 2, they will have the equilibrium temperature equal to 80 degrees centigrade. But here they also have the same amount of water, but the liquid A has a higher specific heat capacity than the B. Let's say it has a specific heat capacity C and this one to C. So let's examine from A. The heat taken by A will be equal to or related to mc times delta T. So as the specific heat capacity of A is bigger, its temperature change will be smaller compared to the previous example. So this will have a thermal equilibrium smaller than 80 degrees centigrade. Insulated cylinder A initially have 150 grams of ice at 0 and B 150 grams of water at 0. To each cylinder 150 grams of water at 80 degrees centigrade is added and left to reach thermal equilibrium, and we're going to compare the final temperature of the mixture. In A, first the ice will melt and then increase to a temperature, but in B I have already water, so just increase its temperature. So B will use all the heat taken to increase its temperature, but A will use some of them to melt. So the temperature of B will be bigger than the temperature of A. So the final temperature of A is less than B.